Hello world and welcome back to my YouTube channel. So this is my second video on my YouTube channel, and in the previous video we talked about evaluating reasoning models, but there were a lot of mistakes that I made in my first video. But in this video I will try to make sure I don't make enough mistakes, and I will go slowly step by step and explain things properly. So in the first video actually I made a lot of mistakes. The delivery method of video, the structure of video was properly damaged. Like there was no proper structure of explaining things. But in this video I will try to make sure I don't make enough mistakes and explain things properly, and I will go slowly step by step and explain things here. So stay with me for maybe next 40 or 45 minutes or maybe 50 minutes, and we will try to learn some of the techniques that we can use at inference to improve our reasoning and to improve our text generation. So I have the proper structure of the video written here. First, we will talk about the chain of thought prompting. That is one of the techniques that we can use at inference to make sure our model can reason better and go step by step and solve the problem and give us the correct solution. And then we will talk about the temperature scaling and a lot of things. So I think the better way to learn these things is to go into the notebook and then go into the maybe go to the whiteboard or something and learn things properly. So I will try to go into this notebook right now here. So in the previous video we talked about the evaluating reasoning models, but in this video how we can improve the reasoning at inference. So there are some of the things that we can use, like chain of thought prompting and a lot of other techniques. So without wasting any time, let's go into the notebook and see things. So first, I actually forgot to mention in the previous video that the base model we are using in the video is actually already the instruction fine-tuned model. And if you want to go and see the model, what kind of model we are using, you can maybe go to the Hugging Face Qwen3 0.6 billion parameter model. I think this is the model. It's not loading properly. I think there is something with my internet connection. I'm sorry. Okay. So this is the model that we are actually using. This is already an instruction fine-tuned model. And yeah, you can see here training stages, pre-training and the post-training. And this is the group query attention. So we're not going to in detail in the core architecture of this model, but we're going to use this. So in the previous video I talked about that we have our own architecture. So what we're doing, we are downloading a model from the Hugging Face, and then we have our own architecture ready, and we are dumping those downloaded weights from Hugging Face into our own architecture. So I think the best way to explain these things is to go to whiteboard or something and explain properly. So let me draw some of the things here and you will get the proper intuition. Okay, so I have this computer that is also, I'm supporting the tablet mode, and I have this type of wrapper pen here that I will use to maybe write maybe draw some diagrams here. So I will start explaining what we are doing actually. So this will be our Hugging Face, okay? Hugging Face. And we are downloading the model from here. And we have our own architecture ready. So you know what the architecture is? That's So we will be downloading these weights from here, from Hugging Face, into our own architecture. So architecture means how many layers are there in the architecture. Like as I told you, it uses the grip query attention. So instead of like downloading the base architecture from the Hugging Face, we have our own architecture defined in the pure PyTorch code, and I will show that code to you, and you can go and later maybe look at that code and maybe get the proper idea how the architecture is defined. So we are downloading this Hugging Face model and dumping those, I mean the weights, into our own architecture. So that means like in the architecture there are a lot of layers, like there is embedding layer and then the whole transformer block and then the output. So instead of like getting that whole code from the Hugging Face, we are writing our own architecture in the pure Python. I mean pure PyTorch and Python, etc. And then we will take the weight of every layer from Hugging Face and then go to our own architecture and copy those Hugging Face layer weights into our own architecture weights. Okay, so I will show you this how it actually works. So I think you got the idea here, like what I'm talking about. Okay, so let me go back and show you where those weights and these layer weights or some other things are actually being downloaded. So if I go back to my Hugging Face model that we are using here, and if I go to the files and versions, you can see this is the model weight, and these are the configurations, the tokenization, the tokenizer config, and the tokenizer.json. And if I go to my code base here, the open source training that I will be sharing the link of this repository, and it is on my GitHub. I will share the link with you. If you go to the base model and then Qwen, you can see I have defined the whole architecture in pure Python. So instead of hand coding, I mean getting that whole Qwen tokenizer from Hugging Face itself, we will define our own architecture. And how we are getting these details is already downloaded from Hugging Face. Like we have downloaded only some of the files that we actually need. So I think model is not properly downloaded here because we didn't run the first cell here properly. It just stuck at 25% and then I interrupted. So I have actually, executed the whole node before. And let's say, give me a second. I think it should be here, but I haven't downloaded that, I guess. Okay, maybe deleted. Okay, let me go to Lightning Studio, and I will show you like what type of model I am talking about. So actually we are downloading this. We're downloading this model.safe tensors file, and inside this file you will see there are a lot of information inside this, like there is embedding layer and the weights associated with the embedding layer, and then you can see all the layers, the input layer non weight, the multi-layer perceptron layer, MLP down projection weight, okay, MLP gate projection weight, and MLP up projection. This is that the feed forward net we have inside the architecture. So you can see this is the K norm weight, K projection weight, output projection weight, and I think it might look a little bit complex. So I think the best way to show this to you is maybe if you know this Sebastian Roschka. He got these amazing architectures, and this is the architecture, I guess. If I can maybe zoom in a little bit. Yeah, so this is the architecture. See how many layers are here. So first we have the token embedding layer, and then there is the RMS layer, and then we have the grip query attention, and then QK RMS norm, and it is using the rotary positional embedding, and then there is a residual connection, and then RMS norm again, then there's a feed forward network, and see all these layers and the weight is associated with these layers, I mean with these blocks. Excuse me. So this is what these layers are like. If I go and maybe click on model dot layers, okay, so we got these many layers. So I think this is the transformer block. Okay, maybe click on the input MLP, and then you can see the post attention layer now weight. So this file will be containing those weights associated with the post attention layer now. Okay, I think the post attention layer norm is this one. Okay, final RMS norm. No, I think this one RMS norm 2. That is the post attention after the masked group query attention. Okay, so these are the weights associated with every block or every technique here used here, like the RMS norm, the feed forward I mean the MLP. You can see the RMS norm 1 and masked group query attention, and if we can expand this group query attention, there are 16 heads, and all the weights associated with the 16 heads. You can see those weights here. Okay, and there is a model layer 1. So this is the one, maybe it got 28 heads, I mean, yeah, 28 heads, and inside these heads, if I go to self attention, okay, and you can see there are 6 heads, I guess. Yeah, so self attention block means this masked group query attention. These are the MLP weights. This is the post attention layer norm, and this is the self attention. So you can see like these are the group query attention weights. K projection, K norm, Q projection, and V projection. Okay, and these are 6, I guess, 16. Okay, we got 6 things here, but these are 16 heads. Okay, got it. So let me explain these things again, what this means. See, I don't know how to like erase this. Give me a second. Okay, so back to our marker. Okay, let's see. So if I take this image from here, like we have some of the things like the token embedding layer, the RMS norm. So let's talk about these things. The token embedding layer, and RMS norm. Okay, let's talk about these two things first. So you can see in the architecture we have a lot of things that the model is built atop of, like as you can see, when we are passing something into the large language model, then that is tokenized, and later on that's passed to the token embedding layer. So the weights associated with that token embedding layer is, so let me see where the token embedding weights. Okay, so these are the token embedding weights. These weights are associated with this thing. I don't know, like if you can see, I'm hovering my one mouse pointer here, embedding dimension of 1024. Okay, so these weights are these weights are associated with these. Okay, and then now let's talk about RMS now. Input layer norm. Okay, this is the input RMS norm. These weights are associated with this one, RMS norm. And then you got masked group query attention. And these weights, these weights are associated with this masked group query attention, and you got 16 heads inside it. Okay, I was a little bit confused what the 6 is, but 6 are, you see the 6 entities here, and it is the Q norm and the K norm, and then you got output projection, and then you got the QKV projection. Okay, yeah, so these are the shapes, and these shapes are also defined in our code. So what I'm going to say that from Hugging Face, we are downloading these files. The file is this file. I mean the model.safetensors. We are downloading this file, and then we have our own architecture ready. See this. And if I show you where this group query, this is our group query attention. Or I can also show you the embedding dimension, where the embedding dimension is. Give me a second. Okay, these are the group, the group query attention projection, like the QKV projection, query, keys and values. Okay, this is the output projection, and this is Q norm and K norm, and that is exactly what we are downloading from here. Okay, how do we go back again? It's taking a little bit of time. Okay, it's taking time. So let me show you what I was talking about. So here it is. I'm inside the Lightning AI Studio that I am using. Okay, see this. I am downloading model.safetensors config.json, tokenizer config.json, tokenizer.json. So these are the files that I am downloading from here. Okay, so let me close them. And you can see the same file is later on being downloaded here, and we have our own architecture ready, and we will be doing one thing, that is we will take all these weights, all these model layer weights, and dump it into our architecture, this architecture that we have defined in the pure PyTorch code or the Python code. Okay, so this is our group query attention block, and this is our feed forward block. So you can see the feed forward block here. Okay, this is our feed forward block. We are using the silo attention activation function, I'm sorry. And you can see we have the final RMS now. We have the QK RMS. We have the rotary positional embedding, and you can see I have also defined the rotary positional embedding. This is RMS now. Okay, this is rotary positional embedding. So this will compute the angles, and this will apply. And I think you have to go a little bit deep inside how the rotary positional embedding actually works to understand it better. So before we were using the traditional sinusoidal embedding, positional embedding, but that was later replaced by the rotary positional embedding. It actually takes the dimension of your, like the embedding dimension, and applies the rotation top of it, sine and cos rotation, and it will first take your whole embedding dimension and maybe split that into two pairs, and then apply the sine and cos, and that sine and cos we are getting from here, cos and sine, and we are applying this to pairs of embedding dimension. Like if you have embedding dimension of, let's say, 64, and it will be into the pairs, so there will be 32 pairs, and inside every pair we will apply the cos and sine. Okay, so I think you have to go a little bit deep inside it, because it's been it's been some time since I touched this rotary positional embedding. So I think you have got the intuition that what I'm going to like what I'm talking about here actually. So this is our whole architecture, and this is how the large language models are actually built there. I mean, you are defining your whole architecture in code, and then you are um, I mean, learning these weights by doing the forward and the backward pass, and maybe doing the training runs. And this is how these frontier models are actually built. And you can see this is the Qwen3 architecture, and it supports this architecture that we are talking about here. And it is mostly similar to Llama 32, I think. And Llama 32 uses the same mask curve query attention with 32 heads, okay? And it got the embedding dimension of 2048, but here in the Q1 we got embedding dimension of 1024. Okay, so I think this was it that I was literally going to explain, and I think I should now close this. And this is, if you don't know, the Sebastian Rosler. I'm following him, and he got this amazing book called Reasoning from Scratch and LLMs from Scratch. And if you are a beginner who want to like go deep into the LLM and reasoning models, post training stuff, or learn about the architecture that these frontier models use, so go check him out, Sebastian Rosler. Okay. So now I hope you got the intuition that we are downloading these weights from Hugging Face, and we have our architecture, and then I have this function here. If you go bottom, you can see, okay, load Hugging Face weights into our own Qwen architecture. Like this is our Qwen architecture. Okay, this is our Qwen3 model, and we have our own architecture ready. What we are going to do, we will compare every layer from Hugging Face and download that weight. You can see these are, we are comparing like QKV projection. Okay, this is with the query projection weight that we will be downloading from Hugging Face, and then we will copy that weight inside our architecture, and then we will load that architecture and we will run the inference atop of that architecture. The architecture will contain the weights from Hugging Face. Okay, so I hope you got the intuition, and I think I should not go deep inside it, so otherwise it will literally ruin the structure of the video. I'm not going to make any a lot of mistakes again that I made in the first video. So okay, so let's get back to our core video structure. So here we will be talking about the chain of thought first. I think we got a spelling mismatch here. Okay. So first, let me exit from here and clean this up. I'm not good at writing because I don't have like the iPad or something here where I can write things. So it's just my computer and it supports the tablet mode. Okay, so now let's go into the and explain chain of thought. So before that, let me show you what we're doing at in notebook first. So we'll be loading the model, and I have to separate function that is defined here in evaluating reasoning models. And inside you can see model and tokenizer, and we will be calling this model and tokenizer function and loading the model and tokenizer here. So please look carefully here which model. This is a parameter that we are telling the function what type of model we are looking for. We are looking for the base model, and this base model will be already instruction tuned model. So it's not only the pre-trained model, but it's already the instruction tuned model. And how we are making this base model into a reasoning model later, that is only by changing this parameter to reasoning. And I think I have literally explained these things how we do this in the previous video, so I don't think like I should go deep inside that again, otherwise it will literally take another half an hour. So first it will be our base model that will be experimenting. Okay, so this is our prompt. You can see we have this math problem, and then we are passing it to the render prompt, and this is already defined here. If you go into the node, the GitHub repository that I will be providing the link in the description, you can see what type of prompt we have. And I think I'm printing this prompt also here. Okay, print prompt. You are a helpful math assistant, solve the problem step by step. And the last line of your response should contain only the final answer inside boxed. So I think I talked about this boxed also in the previous video. Actually, these large language models or your chat GPT always generates text. Maybe if we give some math problem to chat GPT and ask you to give us a correct solution, it will give inside the boxes, but you are not seeing those boxes. Actually, that's already rendered. Maybe this is a latex syntax, but whatever you are seeing in front of your screen is already the rendered output. So in the back end, it is actually maybe generating the latex syntax. Okay, yeah. So I think you might have observed some when you give ChatGPT some math problem, that sometimes if you interrupt the whole response, it might just generate that latex syntax sometimes at maybe during when you exit, or maybe when you stop generation, when you hit the stop generation button, etc. So let's talk about this. So we have our generate text string concatenate. So this will be our inference function that we will be using, and we are passing some of the things here. And yeah, so I think I talked about this stop text and stop after boxed in the previous video also. So we will be using the generate text string with KV cache, and we are importing that, I guess, from somewhere. Yeah, and I think I have already mentioned this or maybe talked about this in the previous video also. So this will be our text generation function, not a big deal to talk about here. This will be our device, and we are just testing it and giving it to the model, and you can see model is directly generating boxed x equals 12. This is not the correct response. And now as the model generated something directly, like I was assuming that model will literally give me some explanation, but it didn't give me the explanation. So now comes the first technique that I'm going to talk about. That is the main purpose of video, to talk about some of the techniques that we can use and improve our responses at inference, or maybe these are some inference time scaling techniques that can literally push model at inference, and maybe use some prompting techniques or scaling techniques or some of other things I will talk about in the coming minutes. So stay tuned here, and the first technique will be, we will be taking that prompt here. This was our prompt. If I go to show you, this was our prompt. This is the math problem, and I'm adding some of additional things here that will be in the new line, explain step by step. So what it actually does, so you can see there is a difference. Without telling the model explain step by step, the model gave me boxed x equals 12 in the latex form. Okay, that means x equals 12. It gave me the answer. But here I'm asking model to explain step by step and solve the problem. And you can see the response that the model generated. Let me think first. I need to solve the equation 3x minus 9 equals x plus 37. So it got the equation and maybe applied some formulas there, and later on it ended up giving me the answer. Maybe also this is not the correct answer, 23, but still see how many steps it thought first. And still is not the reasoning model, we are experimenting with the base model actually. And you can see what is the magic of these 3 or 4 lines, like explain step by step. What is happening actually? So this is actually called the chain of thought prompting. So what actually happens here? Suppose you have a text prompt, and you are asking model to solve a problem. Okay, solve a math problem. So what is actually happening? If I talk to you about instruction fine tuning, and sometimes as I showed this to you, that the model was giving x equals 12, that is the wrong answer. But how can I make sure that without training, or without doing the post training, or maybe without fine tuning a model again on new math sets, let's why can't we use some of the capabilities that model has actually learned in its training set without training it again on other things? So that means we have to push that knowledge that the model already gained from training during the pre-training stage or the instruction fine-tuning stage. So instruction fine-tuning is not like we are getting additional information to the model, but we are asking model like how to generate text, like how to act like an assistant. So what actually happens during the pre-training stage? Model has seen some of the math problems during the instruction fine-tuning stage. Fine-tuning, or also called supervised fine-tuning. Instruction fine-tuning stage, we are not like giving new information to the model, but we are asking it like we are like training it, or maybe we are like telling the model how to behave when the user actually asks you the query. Otherwise it will generate some random text. And that is the power of instruction fine-tuning. It tells the model like how to respond. But there is some lack in this SFT, like the supervised fine-tuning. Like our model can literally solve the math problems. It might have seen the things in the pre-training stage, but it can't solve the problems. And that's why it's giving us the wrong answer. That is boxer x equals 12. So without like, if I got this type of problem, what will I think? Like, should I like train it again, or maybe do some post-training error runs, or maybe like build some like complex RLVR pipelines and maybe train it on the reasoning data? No. So the first assumption that we should think about is how can we use existing knowledge that the model has actually gained in the free training stage. So what we are going to do then, there are a couple of things. When generating text from a base model that's already pre-trained, and then SFT tune like the fine-tuning, like the instruction fine-tuning, that instruction fine-tuning stage actually tells the model like how to behave or how to respond to user queries and act like an assistant like ChatGPT. Okay, but there are some limitations also, like it can't literally solve the math problems. It might like act like a system, but it doesn't have a proper knowledge of the math problems. But how can we like use the existing knowledge that the model might have already accumulated in the pre-training stage? So that's where our first technique comes, that is the chain of thought. So in the chain of thought, we have the prompt and we are telling model extra things, that if I gave you the math problem, you go step by step. You don't have to like go in one go and give me the final answer, but go step by step. Think about the problem. Maybe break the problem into many steps, or explain in the flow. So maybe you might later encounter the correct answer. So that is the first step that we are going to do. So what we actually do here is we have our prompt. This is our prompt, and when it will go to the model might give you the output. Okay, but this output is not correct. This is incorrect. Okay, incorrect. But should I train the model again? No. Why can't we use some of the knowledge that the model has already accumulated in the pre-training stage? So there is this thing that the researchers found, that is chain of thought prompting. That means push the model at inference and ask it to explain things step by step instead of directly giving us the answer. Okay, chain of thought prompting. I'm literally bad at writing, I'm sorry for this. Okay, then we have this prompt, and we will ask model, and we will give some additional information with this prompt and ask model to explain step by step, like we are like teaching a kid like not to make mistakes again and again. Instead, break the problem into small mini steps and see if you can come up with the correct answer. So that is the matching with chain of thought prompting. And when pushing the model with chain of thought prompting, we got this type of result. And you can see the model literally went deep inside the problem and later on gave us a final answer. I don't think like this is the correct answer, but still it gave us some good response instead of getting this x equals 12. That's literally a bad answer. But in our the prompt template, we have asked the model to give final answer inside this box. That will be a number directly, but here you can see the model give us some garbage x equals 12. That's not the correct answer. Okay, so that's why we push the model to think about the problem and break into the mini steps and later come up with an answer. So it gave us the box of 23, but still I don't know if this is correct. Maybe this isn't correct here. I thought I checked it. Okay, so this is the first technique that we talked about, that is the chain of thought prompting. So I think this one is completed now. I hope you got the idea what the chain of thought prompting is. This is the inference based technique, not that like we are maybe pre-training model again, or maybe do the continual pre-training step, or maybe doing some heavy reasoning post-training runs, and that will be costly. So it means why can't we use the existing knowledge of the model? Okay, so now there comes the second technique, that's called the temperature scaling. So what actually the temperature scaling is? Okay, I will go step by step like with the notebook that I have already defined. Okay, first, let's say I have a prompt example that is large language models are. So you know what large language models are. Actually, if I personally talk to you, like not the prompt definition, but let me go to the whiteboard and it will make more sense, I guess. Okay. So LLMs are like some entity that generates the next token. Generates next token. And LLMs are only capable to generate the next token. Okay. So first, how it generates the next token? Like I have the prompt, and that's like you are asking the ChatGPT, large language models are, and ChatGPT might generate the text from there. Okay, so we have a base model and there's already like instruction fine tuned. So I'm only taking some of 4 tokens here. That is large is first token, language models are first, second, third, and fourth. We have 4 tokens, and we will ask a model to generate after this, after R. Okay, that's how the large language model actually work. So first, I'm encoding these tokens into the token IDs, and we are getting the token IDs here. Okay, and then I am passing these input IDs into the model. And what this means, I already maybe talked about this in the previous video, but I will show this again. So I have the 4 tokens, that is large language models are. Large language models are. Okay, and I'm asking model to generate the next token. Okay, so we have the 4 tokens, that is one large language models are. Okay, that's I'm doing inside this code snippet here, and then I am passing this into the model. And what the model will do, model will give me the logits. So what is logits are? The model will give me the next token, next token logits, actually not directly the next token but the logits. Okay, I have 4 tokens here, large language models are. So I have to deal with this token, the last token, that is the R token. Okay, and this R token will give me the next token. When these 4 tokens will be passed to model, I will get the next token. Okay, that's how the large language model generate text in the autoregressive fashion. And we will be taking this last token, that's R token. Okay, I don't know if I can write down this. Okay, this is our last token, or maybe let me erase this all again. So this is our last token. Okay, R. This is our last token. and we have the vocabulary size of maybe 151k. So it means our last token will have the dimension of 151k. Let me check the exact size what it was. I think it is 151,936. 936. So these are the total, I mean the unique words present, those were in the data set during the pre-training stage. I hope you know what is the vocabulary. Yeah, so this R will have 151,936 logits inside it. Like 1, 2, 3, 4, 5, 6, 7, 8, and up to 151,936 logits. Okay, logits. Because our previous token gives us the probability of the next token or the highest logit score. That highest logit score gives us the next token, and I will show you how that works. But here I will also add the badge dimension. That's what the PyTorch actually expects you. You have to add the badge dimension, and inside that badge there might be like a lot of tokens. Okay, so like in our badge we had 4 tokens, and our last token, that is R token, will like this 525 R token ID will give us the next token, and we are passing all these 4 tokens into the model. And then what this means, this bracket colon comma -1 means, it means that from the badge dimension, take the whole badge dimension, because we have only one badge size, and inside this badge size we have 4 tokens, and we will take the last token, that is R token, and from this R token we will get the next token. And how we get that, let me go to the notebook again. Yeah, then what we do, we take the argmax of the next token logits. So it means we go into this vocabulary size, as we have the logit scores from the R token. From this R token logit scores we will get the next token. Let's suppose our next token was here, maybe at 50,000. Okay, 50,000, 136, any random token. Suppose this is the highest logit score is present here, highest logit score, and this torch.argmax will take the highest token logit score index. It will give us the index of that token. Okay, I hope you know this man. And then and our next token is actually pre-trained. Okay, as we have like got the next token from torch.argmax, and then we are decoding that next token by passing it as a list, because we're like extracting it as an item, and then we'll be printing that. I mean, this is the token that's trained. Okay, and it has token ID of 16,176, maybe is present here. This is okay, let me erase this, and 16,176 is the token ID that has the highest logit score. I hope you got it. And then we are like printing it. I'm not like going deep inside this little code things as well. Okay, and I'm just printing only the 100 tokens that are before the train token and after the train token, and you can see the visual. Okay, so this is not something I have to take care of. I mean, go deep inside. Okay, now let's talk about our main thing, that's temperature scaling. What is the temperature scaling? Okay, so here what we do, we are taking these logits, like these logits. Let me clear it again and define these logits again. Okay, this is our R token, ARE, and these are our logit scores. Okay, 151k and some number. Okay, so what it does, let's suppose these logit scores are something, maybe some random float numbers, and what we do, we have the temperature parameter. So what this temperature parameter does, it scales these logits. So have you ever like used the OpenAI API key? Like you might have seen like something, the temperature parameter, and there is a description that if you lower the temperature parameter, the model will give the concise reply, like the concise text generation. It will do the concise text generation, mostly like the correct text generation. Or if you increase the parameter size, it will give some random text. Yeah, that's true. So what actually happens is we actually scale these logits here, and if our temperature parameter is mostly like 5.0, oopsie, let me erase it, will look like 8 otherwise. Okay, let's say our temperature is 5.0. Okay, so what it will does, it will literally scale these small numbers, and these small numbers will be mostly distributed evenly. So what I mean evenly is, if I show this graph to you, okay, this graph, let's see. If I have the higher temperature size and we are scaling these logits with a higher temperature, okay, 5.0, and if you see this, like these blue, I mean the green dots here, you can see like the token logit distribution is like the logit scores are literally, I mean, evenly distributed. So you can see like a lot of difference there. So maybe like all the tokens might get at least like 70 to 80% tokens might get at least chance to maybe get selected as a next token. But when we scale this parameter to 0.5 instead of 5.0, and you will get a lot, I mean lot of bigger change. The model won't be like generating some random text anymore, cause you are literally not giving the model the capability to generate like the next token. So what you are like, what I mean is, you are not literally telling the model to generate random text. So what it does, like, you have these logit scores and you are like dividing them with 0.5, and if you are dividing them with 0.5, so there won't be like a lot of difference there. But if you're like dividing these logit scores with 5.0, there will be a lot of difference. So maybe it will literally scale them up evenly, and that's what this graph is actually showing. So actually this is my second video, and I'm not literally sure like how to explain things. And as I make a lot of other videos, as I make more videos, and I will get better at explaining things. Okay, and let's see this graph actually, and see this orange curve, the orange graph lines here, and you can see like when your temperature is at 0.5, it's mostly sharper, like, and you can see this like this big tower. Maybe that is literally representing the trained, because trained got the largest, the highest logit score that we got from the touch.argmax. Okay, but when our temperature is actually 5.0, it means our logit distribution will be mostly evenly distributed. Okay, and this is our original logits. Yeah, so when our original logit is, you got this blue curve actually, so it means our temperature is equal to 1, and when you are dividing that with 1, that will be exactly same. I hope you got the intuition here. So that is the work of the temperature, and we will see like a lot more details when we go down this notebook. Okay, now let's talk about sampling the next token from a probability distribution. I think it's already here. Yeah, so I think we have already completed this one, otherwise it will literally confuse me later on. Yeah, now we will be talking about sampling next token from a probability distribution. Okay, so what we are doing actually, we are taking these logits, the next token logit, that is, let me clean this again and explain to you again. So this is our last token ID logit scores. Okay, and we are scaling them with temperature, dividing them with temperature. Okay, or let me write it precisely. Logits, logit is divided by temperature. Okay, so it will give us the scalar distribution, but it depends on the parameter, the temperature parameter. If the temperature parameter is 5.0, that means you will get mostly the sharper, the most, let me show the graph again. We will get the flatter, I'm sorry, we will get most flatty. I mean, the flat surface, mostly the distribution will be even. But if our parameter value is, I mean, little less, maybe less than 1, we are asking model to go more greedy and give us the most highest probability token or the highest logit score token. Okay, so I hope this is clear. So score logits, I have defined this function. So this is exactly doing the same that I talked about. Logit is divided by temperature, depends on the temperature value. So we are sampling one thing, and now let me show you what we do after this. So if you know about the softmax function, what the softmax function does, softmax function actually gives you the probability of the token logit distribution actually. So what we do, we pass this logit distribution into the softmax, logits into softmax function, and it will give us a probability. Okay, token probability. Or next token probability. Okay, so this will have the probabilities ranging from 0 to 1, and it will later sum up to 1 because softmax ranges between 0 to 1. I hope you know that. Okay, so we are passing these scalar logits into the softmax function, and it will give us distribution. And you can see, like, I have printed the thing here, tolerance.sum, and we are passing the next token probabilities, and that gives us exactly 1.0. Okay, so we can see the graph when we are passing this into, okay, our temperature parameter was 5.0, and we have passed those rescalar logits into the softmax, and then we got graph like this. Okay, and you can see there's a lot of value, I mean the probability value given to the trainer token actually, that was having the highest logit score. Okay, yeah, and I think you can see it got almost 0.0014 probability, maybe higher than any other token. Okay, maybe at fourth factor. Okay, so this is our token ID 16176, and that represents trained. Actually, our token was if you see this, our input token was maybe large language models are. So our next token predicted is large language models are trained. Okay, the model gave us the next token as predicted trained. That's also represented here in the graph. And you can see we got the next token probability as 0.001. Is it 0.001? Okay, next token probability. What? Let me next token prob, and I think we got the badge dimension here, and then we got the token number 16176, and our 16176 token probability is 0.001, I guess. Yeah, 0.001. That's true. And later, if I so what is actually happening here, what I'm printing here is our next token probability, our next token was trained, and we are passing, when we are getting the probability from the softmax function, that will give us some value. Maybe we got 0.0001, and now I want to check if this is correct with softmax function, as I'm asking softmax function to give me the maximum probability, the token that has the maximum probability. So it gave me the token that has the maximum probability, and the probability is also 0.001. It means our softmax is giving us correct output. Okay, it means that whatever the sampling or scaling we have did with the temperature parameter, and now we are testing it, our next token probability, the trained probability, we are directly passing the index value of that token and asking it to give us a probability of that token, and it gave us the 0.001. Now I want to indirectly check if this is true, and I am asking the next probability, I mean I am passing it into the max function that is already inbuilt max function from Python, and I am passing this whole next token probabilities from 0 to 151k, okay, and then I am asking it to, first I am squeezing it. Squeezing means I am removing the batch dimension, okay, and then I'm asking it which is the token there that has the maximum probability and what is the maximum probability value inside this whole distribution, and that is exactly equal to 0.001. I hope you are it. And then we'll be doing a sample. We'll be sampling a token from Torus multinomial distribution. So what is actually does it literally, I mean, samples one token from the next token probability, and it has sampled 141943, and we have decoded that token later on. It's something called amp, right? Is it Chinese text or something? Okay, anything. Okay, so the next function we are talking about is the count samples. What the count samples will do, it will maybe sample a token from the probability distribution, and then we will be passing those samples into the torch.bin count. What the torch.bin count will do, it will actually be doing one thing. Actually, we're passing the num samples here. So let me explain, go to the whiteboard and explain these things properly, what it actually does. So first, we will be doing experiment 1000 times. And 1000 times we will be doing one thing. We will be passing this 151k vocabulary or the log it distribution, I mean the probability distribution that is representing 151k unique probabilities, okay. And I will ask it, actually we will be sampling from this distribution, and while sampling the distribution I will track everything, like what token got sampled how many times. Let's suppose token 100,001 got sampled 2 times, okay. So that is exactly what we are doing. So we are experimenting 1000 times and seeing that, let me go here. Yeah, so we'll be sampling 1000 times, or maybe we are running a trial, that is we are sampling, maybe rolling a dice 1000 times, okay. And then when we are rolling the dice 1000 times, we are seeing which index value got sampled and how many times, okay. So that is the torch.bin count how often each index was selected, okay. Nothing big here. And then when we are printing that count samples, and inside the count samples we are passing the next token probabilities, the whole distribution 151k unique probability distribution that we got from the softmax, we are passing that into the count samples. And you can see the got sampled 2 times, only got sampled 2 times, known got sampled 2 times, namely 2 times, intensive 2 times, request ID 2 times, and HAM, I don't know what type of text is this, and it was sampled 2 times, okay. So this is actually the demo. But again, when we are now, actually our parameter size was little bit higher, it was 5.0, okay. And this time we are reducing that temperature to 0.35. It means we are literally getting concise, or asking the model to give us the correct answer, not this random, or don't add scarcity inside this log distribution or the probability distribution, but the log distribution, but be deterministic and give us some outputs. The next token the next token has that got the most log score there, and then we are passing that into the softmax, getting the probability load t, okay, probability loading, okay. Then we are passing it into the count samples, and let's see this time what we got. And this time we got, okay, next time we'll log it. We are not passing, let's be careful here, we are not passing this. Wait, just a second. Next token probabilities. Actually I sampled something here, yeah, and then I defined a function next token probabilities CPU, and I pass it probability here, okay. Next token probability, okay. Wait, I'm passing the same thing actually. I'm sorry, I think, but here we are not passing the Next token probabilities, we are passing that into the scale logarithm by temperature first and reducing the temperature to 0.35 and then passing it into the softmax, and this time the model won't be like generating that random text here like these tokens. So otherwise, if the parameter size right here was, the temperature size was 0.35, the model won't be generating these type of words here. Otherwise it will focus more on the deterministic side of token generation. It will be mostly focusing on the tokens that got the most logit, the highest logit score, maybe the first token and the token probabilities after it, or the logit scores after the first token. The token that got higher token, the logit score is trained, and what are the other tokens that got highest token logit scores after train word, and I will show you what I exactly mean later. So here I am reducing the temperature size and asking the model, I am passing then it into the scale samples, and let's see what the result we got. And remember that we are experimenting 1,000 times, like rolling a dice 100 times, 1,000 times. Okay, and after rolling a dice, for example, rolling a dice 1,000 times, we got that 2 times, not 4 times. Use it 55 times, 19x, where he got 19x, and let's see here, we got trained at least 806 times, and if we add these all of these sampling count, and it will be mostly equal to 1,000. Okay, so it means 80% of the times we got trained or sampled, but reducing this temperature to 0.35. Otherwise here the temperature was, I think the temperature was 5.0. okay, maybe it was 5.0. where it is, sometimes it is literally confusing to go into our own node. Okay, here it goes, and we got the rescale and then the next token probabilities. So actually this is my second video, and literally feeling down, like I need some water here to explain things. Excuse me. Okay, and now let's go here, and then we are passing the token ID 16176, and that's our train token, and we are saying that how many times it is sampled, and you can see 80% of times, 80,008, that is mostly equal to 806 times. Okay, 80 times we got it sampled, and now we are adding this temperature scaling to the text generation function. We are adding actually another parameter. It will be taking another parameter, and that's temperature at this time. Okay, generate text temp stream cache. So before it was using the KVK directly. I think let's go to that function again. What it is? Maybe it's in the another notebook. Yeah. So this is the function actually. We were using this text generation function, and this is a wrapper function later on, and now we got this function. Yeah, so this is our whole function. This is a wrapper function, and this is also something that we are, like we had the next token generation with kvget function, where we were like taking a prompt and converting that into token IDs, and then maybe initiating the cache. But here we want to create our new function. Actually this is top pre-sampling, I guess. I went to the wrong function, I'm sorry. Let me go back here. Okay, adding temperature scaling to the next text generation function. Okay, we got this function, and here we are defining these values from scratch. We're not using the concat flex function again, but we're defining every value from scratch, like taking a prompt and into the token IDs, and then model will be into the eval mode, and we'll be doing the inference. We'll be calling this operator, and then we will set model to reset mode, and then passing the token IDs, we'll get the next token. Then we will be having this iterator here, the loop here, that will go up to max new token length, And then if our token temperature is none, then it will simply do the torch.argmax. If not, there is some value inside the temperature, and then we will first scale log it by temperature, yeah, with the temperature value, and then we will be passing those into the softmax function, and then we will be sampling from the, okay, here the num sample is actually 1. We are going to sample only one time because this is our text generation function. This is not the like the demo. I was literally showing this to you recently, but here we got next token equals next to, okay, into the original device where our token ID was, maybe into the our token ID was I mean loaded inside the CPU. So it's not a big deal. We are actually sampling, okay. And AOS token, this is already the same thing, and then yield, that there is a generator giving us the next token, okay. Yeah, so we'll be having the same wrapper function actually, I'm sorry. And then inside this wrapper function we will be having the generation function as generate text temp string. So it is actually a little bit difficult to navigate these things again and again when your notebook goes even bigger and bigger. So you'll literally forget the main things where your text generation function was. So I'm sorry for that. Okay, so this is the second time I'm making a video, and it's almost 1 hour and 6 minutes. I don't know how long it will take to complete the entire video. Yeah, so okay, I showed this to you, like what the temperature scaling is, and this is our function, and when we are adding temperature as 1.1, the model is behaving like this, okay. It is giving us the output as x equals 5, and still the output is not correct. So if I'm going to like decrease this temperature to 0.2, it might give me the correct answer, but I haven't tested with this. Maybe we will test further in the notebook as we go beyond. Yeah, I will show you, like I have some evaluation tests later on, the evaluation experiments at the end. And now let's talk about the top P sampling. And our sampling next token from probability distribution is also completed. And now let's talk about the top P sampling. So let's take this example, like we have a tensor, the toy logits that got 10 values inside it. So what this P sampling actually means, this is another inference time test time scaling technique that literally pushes your model to act more accurately and use its internal knowledge that it has gained from the pre-training stage. And what we do here is we actually first pass it into the scale logits by temperature function, then into the probably the softmax function, and then what we do, we are plotting it here, I'm sorry, yeah, we are plotting it here, and then we will be passing it, wait, okay, now these probabilities, I think the best way to explain these things is to get on the whiteboard, otherwise it will be complex for me. Yeah. So let's say I have this toy probabilities, toy logits, and this got 10 values, okay, 10 values, and these 10 values will be passed into the softmax function, and this softmax function will give us the probabilities for all these logits, okay, from 0 to 10. Yeah, but did you ever thought, as I told you, softmax function will range from 0 to 1, and it will exactly sum up to 1, and that means these 10 values, the probability of these 10 values, the overall all these 10 values will be equal to 1. So it means that not every token is equal to 1, but there are not every logit score is exactly 1. When we pass the logit score into the probability, it means that not every probability of each logit index each token index is exactly 1. It means then, like if we have 10 tokens, it means let's say the token at maybe token at fourth index got probability of 0.7, and token at index 7 got probability of 2, and rest of these tokens, the rest of remaining 8 tokens got probability of 0.1. Okay, and if we later sum up, it will be exactly to 1.0. But now let's arrange it into the descending order. So first we will come up with token index 4 that got the probability of 0.7, and token index 7 that got the probability of 2, and the rest of the tokens will follow. So now what we are doing actually is we will be taking all these tokens, all these 10 tokens, and all these 10 logit scores, then pass it into the softmax, scale it already, and then we will be visualizing it. And first we are going to do the ordering, and we will be ordering them into the descending order, and then we got this target outcome sum that will be the cumulative sum. What the cumulative sum is, for example, I have the requirement here that when you exceed probability of 0.9, stop there. So what it means is, let's say our fourth token index and the seventh token index having value 0.7 plus 0.2 added up to or equal to 9. So it means we will only be considering these two token probabilities, that is fourth index and the seventh index, cause these sum up to 0.9. And when we'll be reaching the 0.9, suppose we got only two tokens that are reaching the probability of 0.9, then we will be stopping. We won't be considering other tokens for the next token generation. Okay, that is the meaning of top P sampling. That means if you got 10 tokens here, but inside our real use case, then we have 151k tokens. Okay, and inside those 151k tokens, let's say we have top P value as we have top P value as 0.8. That means the tokens that got the highest number of probability, and if the cumulative sum of those tokens exceeds the 80% of the probability. What I mean is, let me show you this again. I don't know how to explain these things, as this is my second video again. Okay, we have 151k tokens and we have the probabilities with us. So in our earlier example, we have the trained token. Okay, that was showing us that it got the 80% probability. So that means the one token out, inside this 151k vocabulary size token vocabs, the individual tokens, only one token is there that got 80% of the probability, the sole 80% probability. Okay, so it means the other tokens got 20% probability. Okay, so now what I have, there is a case when the probability of these highest value tokens, so let's say there is another token that is large language models are trained with, let's say there is with word, and with token got probability of maybe 7%. Okay, and there is another one. I will follow the sequence, that is large language models are trained with GPUs, let's say GPUs, and GPUs got probability of 3%. So these are the top 3 tokens, and when I combine their probability, that is 80% plus 7% plus 3%, that is equal to 90%. So what this top P sampling does is, let's suppose we have top P sampling value of top P. Okay, sampling value of 90. So it means, or 0.9, that means, or 0.9, that means we will only be considering tokens that are exceeding the 90% probability, the highest log score tokens or the highest probability based token that is trained with GPUs. So these three tokens exceed the probability of 90 or are equal to 90% probability. So we will only be sampling from these three tokens, okay, and we will ignore rest of the tokens. That is the meaning of top P sampling. That is also called the top P filter, okay. So I think this is already completed now. I don't know like how good I am with explaining things, but I think I am trying literally hard to explain, and I think this video is probably better than the first one because there was no structure of maybe teaching things, and yeah, I think I'm getting better at it. So that's the exact thing we are doing here in this function top P filter. So we're doing the same thing like when our cumulative sum is, I hope you got the intuition of the cumulative sum, or you know what the cumulative sum is. So let's say our trainer token and plus width token is equal to 97, so their cumulative, the running sum is equal to 87% probability, okay. And then when we will add the GPUs, and when we will add the GPUs, it will be 90%, so their cumulative sum is at 90%, and it is equal to the top P value, and it means we will only be sampling out, I mean inside these three tokens, and later on depends on the temperature, what the temperature will be and how the model will react, okay. Yeah, so this is the exact function that is doing that type of work. Cut sample, this is again the same thing. Here our temperature value is 0.35. Okay, then as I told you, like there are few words, I mean the few tokens that got at least the 80% of the probability. Here the top P value is 0.8, that means 80% probability, and our temperature value is 0.39. Almost good, not good, I mean this is a lot of value, okay, not okay. So this is, I mean, lot less value. So exactly, I mean in our first case it was 5.0, okay, this time this is 5.039, that is, it is telling the model that be mostly the deterministic, not at the stochasticity in the log distribution, okay. And we are passing it to the top P filter, and top P filter, top P value is 80%, okay. And the probable, I mean the tokens that are selected here are used typically and trained. So let me go here again and explain these things again. It is, what is it, user typically trained, user typically trained. So these are the tokens that got at least 80% of the probability, okay. And our top P value is 0.8. It means the model will stop maybe sampling, or maybe other tokens will be ignored by the function, the top P filter function, and it will be only sampling from these three words, three tokens, okay. It will ignore the rest of the tokens. And you can see inside this sampling, we are sampling the trainer token 859 times, and it depends on our temperature size, okay. And if I increase this temperature also, maybe it might consider the typically also, or use it maybe if I increase the temperature at 10 or 5. But our top P is 80, so it means these three tokens represent the 80% probability distribution, okay. I hope you got. And then we are, I mean, creating our new text generation function, and that will be using this top P capability, okay. And we are doing the same things here. If there is a temperature, and if there is no temperature, go with the simple torch.argmax. If not, then do these steps again, like log it is by temperature, then pass it into the softmax function, then do the top P probability, top P filter, and then sample from it, and then it depends on the temperature size. I mean the temperature value, how many, whatever temperature value is, and the task or multinomial will sample from that. Okay, and that is giving us the next token. I hope this is clear now. And then when we are doing the inference with this function also, and you can see we got the boxed equals x, boxed x equals 12. So in the previous case, I think we got mostly similar type of result, I guess. Yeah, x equals 5. So it means that the model is literally behaving bad and it is going as a garbage. Okay, now we got another thing that is called the self-consistency. So this is one of the most important techniques, the inference time scaling technique, that is used to maybe push your base model and get at least a correct output. So what is actually the self-consistency, or it is also called the self-consistency what? Self-consistency. So in self-consistency, we are asking model to sample response many times. Like we are asking model to generate 7 different types of responses 7 times. Okay, 7 times. So it will be giving us the 7 responses. Response 1, response 2, response 3, up to 7. So instead of generating only one response, we are generating the 7 responses. And then from these 7 responses, we'll be taking the last final answer. The final answer that we got here. This is our final answer, x equals 12. And this is incorrect, okay? So we are getting the final answer from every response. So that will be equal to 7 final answers. And inside these 7 final answers, we'll be doing the majority vote. What the majority vote means is, so let's suppose response 1 got us value of 5, response 2 got us value of 2, response 3 got value of 5, response 4 got value of 7, response 5 got value of 5, response 6 got value of 0. Okay, I mean the final answer is 0, or response 7, oops, I'm sorry, response 7 got 0. So here we will be doing the majority vote. Majority votes, that majority, I mean the majority vote means what type of final answer is repeating here. I mean how many times the final answer is there. I mean the unique value is there. So I mean what I mean is, so here let's take the example. I don't know like how to explain things like that. This is 5, 5 and 5, and if I like got the count of every final answer, that is 5 got sampled 3 times. I mean 5 got, we got 5 as a final answer 3 times by sampling 7 times, or asking model to generate 7 responses, and inside those 7 responses, out of those 7 responses, we got 5 as final answer 3 times. Okay, it means 5 is sampled 3 times, but this time we are not actually sampling, but we are actually, I mean model is generating 7 different types of responses, and outside those 7 different responses we are getting 5 as final answer 3 times, and that means we will be going with 5 as final answer because it got the majority vote. Okay, majority vote. I hope you got, it's not like that way difficult. And I think this is now clear what the self-consistency vote means. It was literally simple, and I don't know like why people make it so much complex, maybe in explaining the code. Okay, this is also completed, and now let's go to the code. So here is defined something. I have defined something. So don't look at this function, what this does. Okay, we are going to sample 7 times, and we have the temperature value of 0.8, our top P value of 0.9, and rest of the parameters are, let's say. And you can see like sample 1 out of 7, we are doing the 7 different types of generation. Like we are asking model to generate 7 responses instead of only 1, and you can see the model gave us the 7 responses, and inside the first response we got the final answer as x equals 12. So this is some random garbage, and inside second response we got 13, 22, then 12, then 14, then 19, then 12. And you can see I think 12 is maybe 12 will get the majority vote because this is sampler 2 times or it is generated 2 times as a final answer. Yeah, and let's go deep, and because the video is literally getting bigger, and then I'm experimenting it with the chain of thought. Actually what we are doing here, we have the self-consistency function plus chain of thought, COT. So instead of like directly getting this answer, we will ask models to go deep and reason as I showed you in the beginning of this video. It will go deep and maybe take more time and maybe utilize more compute as cause it is going to break the problem into many steps. So go deep inside a problem by using this prompting technique called explain step by step, or call this chain of thought. And so it's not showing the every detail because we are getting the sample 1 out of 7 because we have this actually defined in the function what you are going to print here. Sort of consistency vote here, it will give the sample and the number of out of how many samples are there. Okay, then the answer. Okay, this is our answer. So in the first sample we are getting, I think this is the previous one, yeah, first we are getting 83. Put your number and answer inside box. This is your second answer, the final answer. So this is mostly the garbage, the model is not understanding things. And third time we got 10, fourth time 83, fifth time 83, 37, then 83. And you can see 83 got majority vote, that's 4 times it is generated. And here the temperature value was 0.5. And the text generation, so here is catch. Actually I have written this when I was running the notebook. I was literally I don't know, like we got this type of text many times, and then I disabled the stop text function was disabled because it was literally giving me some problem. I think I talked about the stop text function maybe in my previous video that was evaluating the reasoning models. I got the problem that model was literally considering continuously generating the final answer many times. So I got that problem and I have to stop that, and I used this stop text like if the model is exactly encountering the answer or boxed answer again and again. So I was asking models to stop generation because it was literally wasting compute extra. And yeah, this is not mine. And inside the self-consistency decoding this experiment, as I told you, I was the text generation, the stop text was disabled because it was giving us a problem. And we experimented with temperature 0.8, as I can show this to you. So okay, 0.8, and we got this garbage output, and it is not the correct output. Not anyone is the correct output, not 12 is the correct output. But here when we use the chain of thought with self-consistency, and model gave us 83. I think the 83 is the correct answer of our prompt that I showed to you maybe at the beginning of the video. That was the math problem. Okay, and 83 is the final answer. I think 83 is the correct answer. So I experimented with 80.8 and the model produced some noisy or incorrect answers. Then I reduced it to 0.5. As you can see, the parameter temperature value is 0.5 with chain of thought, and we got 83. That is the correct answer. Okay, now comes our final evaluation. So this is our evaluation function. I will be sharing this notebook with you and the whole code base inside down the description of this box. So we have the evaluation function, and I want to talk about some things. How we are making sure that we run all these, the inference time scaling techniques. First, the chain of thought, temperature, and then top P filter, and then the self-consistency inside one function. So that's why prompt prefix will work, do the work. First, what we do, we are taking the problem from our math 500 dataset that I showed to you in the previous video, and then we will be adding one specs that is explain step by step. That means with the problem I am asking model to explain things step by step. That means the model will do the chain of thought. And our first technique is used in the evaluation function. Okay, now let's talk about the temperature. as temperature, it will take it as a parameter, and top p will be taken as a parameter. So, and what about the self consistency? You can see self consistency. If the number of samples we have to generate, that means we are asking model to, I mean, go deep and generate multiple responses only one time. And if you're asking model to generate responses only one time, that means our self consistency is false default. I mean, we are not going to use the self consistency word. And if we are passing num sample is equals maybe more than one, that will be we are asking model to generate a response many times, and that will be considered as self consistency word. And you can go deep inside it and later on see the whole function. And outside, this is the record, and this record will be here. We are, I mean, writing it to the JSON file, and then we get these type of problems. I mean, the 20 problems as I ran, and you can see ground truth generator function. I hope when you will run this notebook and you will get a clear idea what I am talking about, because when we will be evaluating, I mean executing this function and passing the respective parameter, then it will literally give you these type of things. I mean, what type of problem was there in the data set, what was the ground truth, what was the generated text from the model, and was that the correct answer or not. This is the extracted, what the model extracted by using our previous functions like the extract final candidate, etc. And was this correct? Not. And sample is null. I don't know what the sample parameter is, but okay, this is what we get after running the evaluation. So I hope you got the intuition. I mean, we are using all these things. We are using temperature as 0.2, top p sampling as, okay, top p sampling is default, by default at 0.9, okay, temperature as 0.2, and num samples will be equal to 1. That means we are not going to use the self consistency board. And if the num sample is more than 1, that means we are going to use the self consistency board. And here we will be passing something. So prompt suffix will be explain step by step. It means where you're going to use it, chain of thought. Yeah, and we'll be using the base variant on 20 problems. Our max new tokens will be 2048, and after this the model will automatically stop the generation. Okay, and when we got the first run with temperature equals 0.2, top p sampling at 0.9 by default, and we use the chain of thought on base model, and we ran it on 20 problems, and you can see we got the accuracy of 15%. That is, out of 20 problems, we got 3 problems correct, and it took around 5.8 minutes on Tesla for GPU. And the results are saved here in these files. Yeah, you can later on go and maybe check if you want. I was literally, I mean, watching these things personally, and I was looking at the results, but the generation was pretty good, but the model wasn't like capable of solving a lot of problems, and as we will see and beyond. Yeah, so inside our first eval, we got 3 problems correct, 15% accuracy, runtime at 5.8 minutes for 20 problems, and we were using the Tesla for GPU. And similar things are written here also. Okay, and I think I have explained these things. And inside the eval experiment 2, on the base model, we are using temperature parameter, I mean temperature at 0.2, and top p sampling is same again 0.9% by default, and then we are using the chain of thought with self consistency as number of samples will be 7. It means we are going to ask model to generate a response 7 times, and we are using these inference time scaling techniques, of course, temperature, top p sampling, and self consistency word, chain of thought. Okay, on 20 problems again, and this is our chain of thought suffix. Number of samples will be 7, and temperature will be 0.2, top p will be 0.9. And this time what the result we got 4 problems correct out of 20 problems. Okay, and we got accuracy of 20%, and it took us around 36.6 minutes for 20 problems on Tesla for GPU by asking model to generate 7 different responses for every problem, and doing the self consistency board. I mean, generating 7 responses for every problem. I'm sorry. And this was our result from eval 2, chain of thought plus temperature plus top p, that gave us 3 problems correct out of 20, accuracy with 15, and took time of 5.8 minutes. And then when we used the self consistency num sample is equal to 7, if we got 4 problems correct and 20% accuracy, 36.6 minutes. But what we observed here is self-consistency was literally maybe improving the accuracy from 15% to 20%, but it was literally using a lot of compute. You can see from 5.8 minutes, it was jumping literally, I mean, beyond my expectation, because it took us a lot of time, but it didn't give us a lot of correct results. Like if the result is for like maybe a sample of 15 problems correctly out of 20 problems, that then I might have gone with the self-consistency, but the results are still bad. Maybe it improved the accuracy a little bit, but still it's bad. I only one problem it got correct more than the base experiment, that is COT plus temperature plus top P. So this was literally bad, and then I ran into the reasoning mode, and I hope you know about the reasoning mode. I talked about in the previous video, I guess, where we were enabling the thinking tags inside the assistant generation tags, and that was cause the Qwen3 got this capability. You don't need to like download the separate reasoning model that is maybe instruction tuned on some reasoning data. Actually, what we do, we enable those thinking tags using the tokenizer. I think I have discussed that in the previous video, I guess. Yeah. And here which model will be equal to reasoning, and I'm not going to deep inside that. And I will be again experimenting with 20 problems. Our parameters will be same, temperature at 0.2, top P 0.9, and this time our num samples will be only 1. That means we're not going with the self-consistency vote again, because that will literally exhausting our compute level. And this time you can see we got 3 problems correct. So it means the reasoning model is not literally showing us some new improvements, but the average response length is 93.12. In average, the token generation length was 93.12. Is it per minute? I guess. I think it's per minute. I guess. Yeah, in average. Maybe per problem. Okay, maybe per problem the average response length. Okay, I mean anything. That's not a big deal. So from the eval 3 result, we got correctly 3 problems correct out of 20 problems. Accuracy is same like the first assumption, but this time did we use the chain of thought? Yes. So I think the result is still the same with the reasoning and the base model by using the chain of thought, temperature, and the top P sampling, and it again was executed on the Tesla GPU. So the key observation, what was here, reasoning more generated efficiency, longer reasoning traces, maybe 493 tokens on average, or is it per? I'm a little bit confused, like tokens on average. Okay, maybe it consumed 490 tokens on average per problem. Yeah, but did not improve accuracy or base configuration together with the self-consistency. Okay, this is exactly what I discussed before. All of the experimenters, the model showed limited mathematical reasoning ability on the first 20 problems of Math 500. Adding chain of thought prompting encouraged the model to generate longer reasoning traces. And self-consistency only improved from 15 to 20%. That was in the good gain, because it was using the higher computational power. So what we learned from this experiment is that when we are using the chain of thought, maybe temperature and top P sampling, maybe it is performing better than the base variant instead, because the base variant was literally performing bad. That was it giving us the correct output, even not the final answer, inside that box correctly, but giving us some garbage. But when we use the chain of thought, temperature, and the top P sampling, the model gave us a lot of correct answers. Not it performed better on all these 20 problems, but at least gave 3 or 4 problems correct. And maybe sometimes it just generating some random garbage. And you can maybe go into these JSON files and see what type of text generation it did. This is the generated text, and a lot of times it just maybe generated some garbage like we were getting from the base variant without the chain of thought, etc. So this is the final, then put the final answer inside box. That is what it got as a final corrected answer. So this is again, I mean, you can get some garbage here. Okay, that's why we didn't got a lot of accuracy, because model wasn't literally, I mean, understanding the things, but we were asking it to do. So this was all from our experiment of 3 evaluations. I mean, we ran 3 experiments and we saw like why the model was literally struggling, and self-consistency literally was performing bad on these problems, because it was literally, I mean, consuming more compute power and taking more time. But I think the big gain we got was from the chain of thought prompting. And I think that's all for this video, and I think I should maybe leave now. It's been maybe 1 hour and 40 minutes. Oh, see, oh my god, this is a lot, and I think I should wrap this video right now. And I hope you liked this video. This is my second video, and if there are some delivery mistakes, will you let me know in the comments. If you are watching, I don't know, like, will people literally watch this 1 hour and 40 minutes video? I will be posting it on the LinkedIn and x.com. And yeah, so this is my second video, and in the coming videos I will try to maybe make these videos at 20 to 30 minutes long, not go deep inside everything, maybe explain things and share the notebooks with you, so you later on maybe explore yourself. So I think this is all from my side, I guess. And maybe thanks for watching. Thanks. Okay, this is how I write. And have a great life, and if you want to explore this, I will give the link in the description. Okay, yeah. So let me tell you about one thing. If the model literally, I mean, performing bad at inference, even when pushing it with these inference time scaling techniques, then there might be need that we might have to post train again, I mean, fine tune again, or maybe do the preference optimization or the reinforcement learning runs, etc. Maybe use some new math based data and build a reinforcement learning from rewards pipeline, and maybe further do the RL training. And maybe, because RLVR is known for making these base models, I mean, literally, I mean, the beast is I can see the beast, like, because there is a lot of improvements with the RLVR, because all these frontier open weight models like the DeepSeek and all these Qwen models are literally trained on that same pipeline, the RLVR pipeline, and we can see a lot of dramatic change, I mean, the dramatic gains on base models by using the RLVR, because it's literally, I mean, making a base simple model of frontier model, and it can literally later on break or beat some of the frontier top tier labs, the models from top tier labs, and so many benchmarks, I mean, the top tier benchmarks. So yeah, I think this is all from me, and we will talk about more inside this RLVR. And I have personally not explored a lot of things inside the reinforcement learning for LLMs right now, and I'm going deep inside, and I will be learning with you. But I have some base knowledge, I mean, that I can share with you, but I want to go deep, because my field is in the post training, and we'll be going deep together. Okay, so I hope this is all from you got the intuition, and this is all from my side. So this is my second video, and I hope I made some of the mistakes here maybe delivering this video, but in the next video I will try to maybe optimize more. Yeah, so thank you, God bless you, and have a great life.